Okay, so now that we've sort of recalled the motivation for using the definite integral to find values and what that means spatially, we talked about with area, what we're going to be doing in section 6.1 and 6.2 is extending that one dimension to find, to use the definite integral to find volumes of solids. So let's kind of consider some sort of a solid blob that's sitting in space. So if we were to, now this is a little bit tricky because we're trying to draw 3D in on a 2D space. So if we drew our y-axis here, so this is y, and now I'm going to kind of push this x-axis out a little bit. So kind of imagine that this is kind of coming out of the screen at you. So this is our x axis. And then I'm going to draw a little, just sort of a little blob here that exists on the axis. So again, nothing too special. And it's three-dimensional, so we could kind of give it a little bit of shading here, just to kind of indicate that we're dealing with something that's floating in space. All right, and so let's say that this little blob exists on the x-axis or above the x-axis between, again, point A and then all the way out here to point B. So it lives right above that. Now, kind of in the same vein as what we did with finding area, let's go into this blob and take a section of that. So we're essentially going to be kind of slicing a slab out of this. So almost think about it like you go to the grocery store, to the deli counter, and they're going to slice slabs off of a larger piece of meat that you're getting. So what I'm going to do is I'm going to go in and remove, or at least highlight, a particular section. So let's go in here and I'm going to highlight this part of our solid. So almost think about it like we're kind of cutting it out, and it's got a circular shape, and it's kind of highlighted. So we took this band and we're essentially removing it from this solid. So I'm going to kind of look at this right here, and just so we can kind of bring it off to the side. So this is what we're, oops, sorry about that. This is what we're sort of focused on right here. Is this slab, and that was the surface of the area. So how do we find the volume of this cross section of the slab? Well, once again, we could define the width. So that would be this distance right here. This is the width of the slab. And we could go in and say, well, that's from x sub k minus 1 all the way to x sub k. So very similar to the way we did it with area under a curve. So let's go ahead and start taking note of these. So the width of this slab is going to be x sub k minus 1 minus x sub k, which once again we're going to refer to as delta x sub k. Now, to find volume, it's not as simple as just measuring the height, but what we could do is we could measure the surface area of the top or bottom of this shape. We can't see exactly that it's circular right now, but it's some sort of a geometric shape. So we're going to really kind of generalize this for now. We'll get a little more specific when we get into more examples, but for right now we're just going to say we've got the width, and then we are going to consider the surface area of the top or bottom. It's not going to matter eventually, but I'm going to call this A of x sub k. So that's some formula that we don't know necessarily for right now for the surface area of the slab. So if we wanted to find the volume of the entire solid, Let's consider this. First, we would start with the volume of the kth slab. I wish there was a more rigorous term to use, but that's the best that I can think of. So the volume of the kth slab here is going to be V sub k is equal to whatever the surface area formula that we have is times delta x sub k. So it's the product of those dimensions that will give us a three-dimensional volume. And if we wanted to find the volume of the entire solid, once again, what we're going to do is we are going to consider, well, as the number of slabs, and we'll just say that that's n, approaches infinity, then what we can do is we can say that the total volume is going to be equal to the limit as n goes to infinity of the sum of each of these slabs. So from the kth slab to the nth slab. And again, those volumes are a of x sub k times delta x. And if we can kind of figure out now that this is looking a lot like how we transitioned from Riemann sums of rectangles to the definite integral. And what this will end up giving us is the definite integral from a to b of a of x dx. And this will be how we calculate volume. So it's worth considering at this point, what are the things that we need to actually calculate this volume? So let's make note of this because this is going to come in helpful, particularly helpful a little bit later. So we will need two things. Not to oversimplify, but we're going to really need two particular things here in order to calculate this volume. The first thing that we're going to need is we're going to need a formula for the area of a cross section, where we refer to it as a slab in this case, but more generalized, we're going to refer to it as a cross section. And then two, we are going to need the bounds, A and B. So as we move on to these next more specific topics, it's always good, I think, to kind of keep this in mind, that when we start talking about finding volume, this is how we do it. These are the two things that we are going to need to gather before we can proceed with calculating a particular integral.